Okay, so here in this video, we are going to take a look at concavity and using the second derivative test to determine concavity. So first of all, we have to know what concavity is. What does that mean? In geometry, you learned about the concavity of objects, but this is going to be a little bit different because we're looking at the graphs of concavity, whether a graph is concave up, concave down at different points. So what does it mean if a graph is concave up? Well, in simplest terms, is concave up if the derivative is increasing. So if f prime is greater than 0, then it is concave up. And these mean the same thing. The derivative is greater than 0 or increasing, they mean the same thing. Concave down, it means the opposites. So if the derivative is then less than 0, which means it would be decreasing. The derivative is increasing, the derivative is decreasing. What that might look like on a graph. So here we have a simple graph, something like this. If you sketch the tangent lines at different points moving left to right, and think about the slopes of those tangent lines. They start out negative, like that first one was negative, then it's about 0, and then they keep getting bigger. So the slopes, right? All the slopes are increasing. And I should up here, just fix this real quick. If the second derivative is greater than 0 and the second derivative is less than 0, it's increasing, decreasing, right? So in this case, since these slopes are always increasing, then that would mean that our second derivative is always going to be bigger than 0. In a case like this, it's concave up. Now an example of concave down, right? If we look at different points on this graph from left to right and think about what those slopes are, now these slopes are getting smaller in value as you move from left to right. They're getting smaller and smaller, right? So the slopes are decreasing. And so that means your second derivative is less than 0 or it's concave down. Okay, so the test for concavity is rather pretty simple. You have to find, that's the first thing you do, is find the second derivative of the function. Sometimes it's easy, sometimes it involves a little bit more. But if you know that the second derivative is greater than 0 on the interval, whatever that interval is, then the graph is concave up. Now, if the opposite of truth is true, the second derivative is less than 0 on the interval, then the graph is concave down. And remember, if it's concave up, it kind of looks like that. If it's concave down, it kind of looks like that on the interval. Sometimes it can be very difficult to tell, sometimes not so much. Let's take a look at this next one. Determine the open intervals on which the graph, so here's your graph, is concave up or down. And we're going to try to do this without a calculator. Okay, but first thing I want to do is look at what the graph is. So if we could graph it using a calculator first, but the graph looks something like this. Okay, it does change concavity in there twice. So somewhere in here, it goes from concave up to concave down. So increasing slopes to decreasing slopes, and then decreasing slopes to increasing slopes somewhere in there. And we don't know what these values are. So that's our goal, is to figure out what those are. So it has to deal with the second derivative. So go ahead and take this function right here and find the second derivative and set that equal to 0. Try this on your own. Pause the video and then come back. First derivative, when you simplify it, the first derivative should be something like this. You can rewrite it with the x squared plus 3 squared up top, but that exponent would be a negative. So go ahead, if you're this far already, find the second derivative. If not, if this wasn't right, start here and find the second derivative. Low d high minus high d low all over low low. The quotient rule, you get something like this. Now remember, we're setting this equal to 0. So if you look at the denominator, this can never be 0, because there's no way to get a negative answer right there. So you can ignore the denominator right away and only focus on the numerator. So focusing on the numerator, simplify that down and set it equal to 0. You should get something that looks like this. I can't simplify too much, but on the right side, multiply everything in, simplify, put together like terms, you end up with just positive 48x. So you're wondering where that comes from, because all of these, let's see if I can erase that, all of these had x squared plus 3. So I ended up taking, to make my job simpler, taking this out. So that would be to the 0 power, made that down to the third, and made that just to the first power, right? Because they all had an x squared plus 3 in it, so I took one out of every single term. So that's how I was able to get it down to here. Now, once you're here, it's equal to 0. You can take, I'm going to take this to the other side since that's negative. So you would have then 48x squared is equal to, we can multiply this, and if you wanted to, that would be 12x squared, negative 12x squared minus 36. And then if I add 12x to each side, as I took it over, this would actually be positive. So that would be positive 12x squared and positive 36. So I'm going to subtract the 12x squared. So you get 36x squared is equal to 36. Divide out that 36. That's a 36. So you end up with x squared is equal to 1. So x is equal to positive negative 1. So that's what these inflection points, these are called inflection points, and we'll define those in a minute. But that's where these inflection points occur, where it goes from concave up to concave. So concave up, concave down, back to concave up. And again, if we didn't have the graph, if you had to do these with a calculator, just go back to when we learned the first derivative test, right? To tell when functions are increasing or decreasing, we tested points. So we're going to test points on each side. So I would choose like -2, 0, and 2. Okay, and you're doing this is a second derivative test. So it would be the second derivative at -2, the second derivative at 0, and the second derivative at 2. And again, all you care about, you're going to plug it back here, and all you care about is if it's going to be positive or negative. When you plug in -2, you get a positive answer. When you plug in 0, you get a negative answer. So positive here, it's negative, positive. So it's concave up, then it goes to down, it goes back up. So it should look like up, down, back up, something like that. That's beautiful, right? But you can see that's what our graph somewhat looks like. Plus. All right, so if you don't have the graph, you can still use the second derivative test points on each side of those points of inflection. Again, we will define those in a little bit, but those points where it changes from positive to negative are called the points of inflection. Let's look at this one, strictly looking at the graph. So first thing, because if you find the second derivative of this, it's kind of a beast. Doesn't look that bad. The first derivative is not that bad, but the second derivative is kind of a beast. So let's go ahead and just graph this on your graphing calculator and sketch it right here. Pause the video, graph this, sketch it, and then come back. First of all, if you just think about what the graph is going to look like, we know that there's a discontinuity, and this is equal to 0, which is at 1/2. So let's do x is equal to 1/2, and there's going to be an asymptote there. And then also, if you look at the limits, so as x approaches positive and negative infinity, that's your end behavior of the graph. It's going to look like, if you take the leading terms, so x over 2x, take the leading terms and simplify the x, right? That's just x over 2. And so if you graph something like x over 2, your graph is going to follow that in terms of end behavior. And you should see that your graph is going to look something like, I think it pops over, but it leads it. So purple right there is what our graph is going to look like. Okay, now if you look in terms of concave up, that means where are my slopes increasing? Right, second derivative is greater than 0 where my slopes are increasing, and that is going to be on this left side right here. So it's going to be concave up from negative infinity up to 1/2. And then concave down from 1/2 to infinity. Because on this side over here, your slopes are always decreasing. They're getting smaller and smaller and smaller as you move to the right. We talked about the points of inflection, and so what we'll do is we'll define points of inflection here, then we'll start another video to go over an example or two of points of inflection. But a point of inflection, remember, it occurs where the second derivative is equal to 0. So in order to find it, find the second derivative, set it equal to 0, right? And a point of inflection is where the graph goes from concave up to concave down. Is if you find the point of inflection, you set the second derivative, set it equal to 0. It could look something very much like what we've been doing. Sorry, let me do a better one here. So it goes from concave up, and then at some point in here, it goes to concave down. Right at that point, that is your point of inflection. It would look like that. And you notice your tangent line. This is where the first derivative isn't very useful, but your tangent line right there has an m value. Another example of a point of inflection, it goes from concave up, and then all of a sudden, concave down. Concave up, and then all of a sudden, concave down. There, it has a horizontal tangent, right? So something at some point, you notice that the horizontal tangent is where the point of inflection are. So in that case, both the first and the second derivatives are going to be equal to 0. And then the last way would be a vertical tangent. So it goes up to down. So right in here, where your first derivative is undefined, and your second derivative could also be undefined, or it could be 0 to identify that point of inflection. So 3 different ways that that point of inflection could look. Okay, so in order to find a point of inflection on a graph, here, all you do is set the second derivative equal to 0 to find your points of inflection, right? If you are just looking at the graph, you might want to look at some of these examples up here where the slopes go from increasing to increasing, where that breaks. Looking at your tangent lines. Without the graph, that might be actually here where this goes, where the second derivative is equal to 0 without the graph. Determining on the function, sometimes it's easier to look at the graph. Like on this one up here, if you go through and define the second derivative, it's going to be a beast, but some of them aren't that bad. This really depends. It might actually be faster to do the calculus versus just graphing it. And that's the end of this video. We'll come back and do a couple examples.